Section 1.3, we're going to use segment postulates and measure distances. A postulate is a statement that we must accept without proof. This is a statement that's always true. These are things that don't need to be proven, and most of the time you'll find they're common sense things. They'll make sense without a formal proof. The word at the bottom is axiom. This is another word for postulate. So you may see this in another geometry book, or if you take a geometry course somewhere else, you may see the word axiom. It means the same thing. We're going to start with distance or length. Distance is a measurement from one point to another, and this is always positive. So make sure when you're asked to find a distance that you always have a positive answer. We'll find distance two ways. The first distance formula is the distance between 2 points on a number line. And to find this, the formula is at the top. This is the absolute value, those are absolute value bars, of A minus B. Order of operations says we do the stuff inside the absolute value bars first. So we'll actually subtract the two numbers, A and B represent the numbers, in whatever order you'd like, and then we do the absolute value, which just guarantees that that answer is positive. So if it's a positive inside, it comes out, it stays a positive. If it's a negative, remember that when it comes out of the absolute value bars, it takes the negative sign off because absolute value is the distance from 0. So if we look at number 1, we're going to do the absolute value, and you can subtract these in whatever order you'd like. So if you'd like to do 11 minus 7, knowing that you're going to get the absolute value of 4, then our answer is 4. If you did 7 minus 11, you'd have the absolute value of negative 4. You would still have 4. Make sure none of your answers still have the absolute value bars on. You need to go ahead and use those and give one answer. The second one, we want the distance between negative 4 and 12. So I'm going to do negative 4 minus 12. And remember, you can always change this to plus a negative. So we have the absolute value of negative 16. So the distance is 16. We want to make sure our answers make sense. So when you think about this, think about on a number line, there's 0, how far it is to get from negative 4 to 0. There's 4 spaces, and then over to 12 would be 12 more. So 4 plus 12 gives you that 16. Number 3, the distance between negative 5 and negative 12. Negative 5 minus negative 12. Minus a negative turns into plus a positive. And we're doing this inside first. Negative 5 plus 12 is the absolute value of 7, which is just 7. And again, make sure you don't leave any absolute value bars in your answers. We always want to use those and leave our positive answer. We're going to use two postulates. The first postulate in the book is called the ruler postulate, and we can read through that book definition. But what this postulate says is that there's one number for each point. If you look at a number line, on each tick mark on a number line, there's one number. There's a mark at 0, and then there's a mark at 1. There's not more than one number at each one. There's one positive distance between any 2 points. So if I asked you for the distance from 0 to 5, you're going to tell me it's a positive 5. There's only one distance, and it's always going to be positive. We'll use the term between a lot when we talk about points. When 3 points are collinear, and remember from yesterday that collinear means on the same line, one point must be between the other 2 points. One is tracked. So if I have 3 collinear points, 3 points that are on the same line, A, B, and these are capital printed letters because they're points, then one has to be between the other 2. B is the one that's between because it's the one that's trapped. Postulate 2 is the segment addition postulate, and we need to know the name of this postulate for when we start proofs. So you'll hear segment addition postulate a lot. The segment addition postulate says, like our picture we just drew, if B is between A and C, B is the one that's trapped, then, and I'm going to stop for a minute and talk about what happens if we list the 2 points without a symbol above. We talked about if we had AB and there were arrows on the line, that was line AB. We said if it didn't have the arrows, that's segment AB. If you leave the symbol off completely and you just list the two letters, what that refers to is the distance from A to B, or the length of segment AB. So this says the length of AB, so from here to here, plus the length of BC, from here to here. If I add those up, I get this whole length from A to C. Segment addition says if you add one segment plus one that's right next to it, then you get the whole large segment. Number 2 says A to C is 12, and that's the whole length of those two segments. From A to B is 4, and it wants us to find the length or the distance from B to C. If the entire segment is 12 and A to B is 4 of it, this would be a subtraction, and BC would be 8, because 12 minus 4 is 8. The next few problems we're going to do true or false, and we're going to think about whether or not adding the lengths of the first two segments would add up to the third one. For example, if we look at number 1, it says the length from A to C in blue on the number line, plus from C to E would be the same as going from A to E, and that is true. We want to make sure when we look at these lengths that there's no gaps, there's no missing spaces, and there's no overlaps, that no segment is being counted twice. Number 2 says the length from A to C, so I'm going to put that in red, plus the length from D to F, and I'll put that in black, adds up to the entire length AF. Well, if we look at A to C and D to F, putting those two together is not the same length as AF because there's a gap. So this one is going to be false. The first problem we said was true, but we did not write true on the slide. So let's go back. That was true. Okay, so number 2 is false because there's a gap. If you find a gap or you find an overlap where a segment is used twice, it's going to make these statements false. Number 3 says the segment FD, and I'll put that in red, so F to D. And remember, these lengths can be listed either way, D to F or F to D. It's the same thing for that segment. Plus the length of D to B is equal to the length of the segment FB. So we're going to look at those two added together. There's no gaps, there's no overlaps. Another thing you can look for is there should be a letter that repeats. That's where the first segment stops and the second one begins. And then it's the outside letters, taking away the repeating one, that gives you this entire segment. So there's some shortcuts. This one is also true. If I add those two up, I get the whole length from F to B. Number 4, the length of segment BD, or the distance from B to D, plus the length of segment CE, or the distance from C to E, is the same as the length from B to E. Well, if this, let's say maybe every segment's 1. If I added all of these up, this is 1, 2, 3, 4. And B to E is only 3 spaces. Those aren't the same because this segment CD is being counted twice. So there's overlap here, which makes the statement false. Adding BD plus CE is actually going to give us a longer length than just from B to E. Again, there's no repeating letter, so that's something you can look for as a shortcut. The next kind of problem is actually not true false. These are going to be problems that we solve. Point B, and I know this is a point because it's a capital printed letter, is between A and C. So if we look at our picture down here, B is between A and C. So B is the one that's trapped, it's stuck. The length of AB is X. The length of BC is X plus 6. Right here. Then they tell us that this entire length of AC is 24. So we're going to use the segment addition postulate. Segment addition says the first little segment plus the second one adds up to the whole length. So if we take x plus 6, it should add up to the entire length 24. We're going to write an equation, and I'm going to flip to the next slide to write this equation that states that x, this first length, plus x plus 6, the second segment, adds up to the whole 24. So we have x plus 6 equals 24. Then using what we know about equations, we're going to combine our like terms. X plus x, this is 1 plus 1 is 2x. And then we'll solve for x. So to get rid of adding 6, we're going to subtract 6 from both sides. 2x is 18. 2 and x are against each other, they're multiplied, so we'll divide by 2. And x is 9. Now, using what we just found that x is 9, we're going to go back and see if we answered the problem. We know that x is 9. This says find the length of AB and find the length of BC. So I'm going to write down what we're looking for. We're looking for the length of AB and I'm looking for the length of BC. Well, AB was just x and x is 9. So AB is 9. BC is x plus 6, but x is 9. So 9 plus 6 is 15. And I can double check my answer because adding those two small segments, 9 plus 15, does give me a total of 24. And that's a way that I can tell I got the problem correct. Two definitions we're going to use. We're going to use the word congruent a lot in geometry. Congruent means that two objects have the exact same shape and the exact same size. So same shape and same size. Now we will talk about things that are similar. They have the same shape but they're different sizes. To be congruent, it must be the exact same shape, exact same size. And in the parentheses, that's our symbol for congruence. It's an equal sign with, we can call it a squiggle, or if you take Spanish, it's like a tilde on top. Congruent segments then would be two segments that have the same length. They're the exact same length, kind of like our two little bars in our congruent symbol. Again, take a moment to write those down. We're also going to use the Pythagorean theorem and do some review with this from algebra for right triangles. Remember, your Pythagorean theorem works for all right triangles, and we can actually use this to show that triangles are right. And we use a squared plus b squared equals c squared. Remember, the a and b are the legs, and you can call whichever one you want a and whichever one you want b. C is always the longest side, it's the hypotenuse. And there's a theorem in geometry that says the longest side is always opposite, it's across from the largest angle. Since the triangle is 180 degrees, this 90-degree angle is the largest angle, so across from that, opposite it, is the longest side. So we're going to plug our parts into the Pythagorean theorem and make sure that we solve using the order of operations. So our first example, this is a right triangle. And we know that A is 3, B is 4, and we're finding C. We're just going to plug into the formula, and it's up at the top of the slide. So A is 3, so 3 squared, plus B is 4, 4 squared, equals C squared. And we want to do these exponents first. When we think about our order of operations, we do anything inside parentheses, exponents, multiplication and division left to right, then addition and subtraction left to right. So we need to do our exponents first. 3 squared means we're doing 3 times 3, which is 9. 4 squared is 4 times 4, which is 16, equals c squared. 9 plus 16 is 25. Then when we talked in algebra, the opposite of squaring something is doing the square root. So when you get the c squared and you want to find c, you're going to take the square root to cancel out the squared. But if we do the square root of the right side, we also must do the square root of the left side. And again, we're only looking at our positive, our principal square root, because these are lengths, they're distances, we can't use negative answers. So for the square root of 25, we'll use 5. And we'll talk in class about what's special about this 3, 4, 5 right triangle. The next one, we know that a is 4, so we're going to use 4 squared plus b is 6. 6 squared equals, and again, we're finding c. Pay really close attention to which letter is missing when you work through these problems. That one needs to stay the variable. 4 squared, 4 times 4 is 16, plus 6 squared, 6 times 6 is 36, equals c squared. Again, we're going to add up the 16 and the 36, and we get 52 equals c squared. This time when we do our square root, 52 is not a perfect square. It doesn't give us a nice exact answer. So this is where instead of using our calculator and all those decimal places, we want to go off to the side. So I'm going to go over to the top right hand side of the slide and do our factor tree. So for these examples, we're going to find the distance between the 2 points using that distance formula. So I'm going to write the distance formula down. D equals big square root x2 minus x1. And remember, those are subscripts. Just telling you what order to subtract the x's in and subtract the y's. Also remember in your points, point A is 3, 4, that's x, y. Point B is 5, 8, that's x, y. So we're going to keep our big square root, and we're going to subtract our x's. And you can start in whatever order you'd like. I'm going to do 5 minus 3. And then we want to keep the y's in the same order. Since we started with 5, I'm going to start with the 8 minus the 3 was second, so the 4 will be second. After this, it's order of operations. Underneath our big square root, we're going to do our parentheses first. 5 minus 3 is 2. In this parenthesis, 8 minus 4 is 4. Then we'll do our exponents. 2 squared, 2 times 2 is 4. And 4 squared, 4 times 4 is 16. And we add those up, and we have the square root of 20. Again, all of these answers need to be in simplest radical form. Do not write down the decimal. So I'm going to go off to the right, and I'm going to break apart. I'm going to do a factor tree with 20. I know in red that 20 is 5 times 4. 4 is 2 times 2. And again, I broke apart the 4, so it's gone. We have a pair of 2's, so the 2 goes outside. Our lonely 5 stays underneath. So our final answer for the distance between 3, 4 and 5, 8 is 2 rad 5. Number 2, we want to find the distance between the point 74 and the point 39. So again, distance formula looks like this. You're subtracting your x's, squaring it, subtracting your y's, squaring it, and then we're going to add those up. So big square root, my x's are 7 and 3. And again, you can do this in whatever order. You could have done 3 minus 7, as long as your y's stay in the same order. Since I started with 7 this time, I have to start with its partner 4. Inside the parentheses, 7 minus 3 is 4, but 4 squared is 16. 4 minus 9 is negative 5. Anytime you square something, it's going to turn out positive. When we do negative 5 squared, negative 5 times negative 5 is a positive 25. And this is a good place to stop and make sure you're adding two positive numbers. That tells you you squared it correctly. 16 plus 25 is 41. So we have the square root of 41. Do our factor tree. Something that goes into 41. I'm stuck. 41 is a prime number. That is our final answer, just the square root of 41. Number 3 says we want the distance between the point -2, 3 and the point 5, -1. I'm going to plug in my two x values and my two y values. So the x's are 5 and -2. Since I started with the 5 on the x's, I have to start with its partner y, -1. And be really careful with the negatives. We did a positive 5 minus from the formula the -2 that was at the top. Here we're doing the -1 minus in the formula and the 3 that's at the top. 5 minus -2 turns into plus a positive, so we'll have 7 squared plus -1 minus 3 turns into plus a negative, so we have -4 squared. 7 squared, 7 times 7 is 49. -4 squared, again, and -4 times a -4 gives you a positive 16. When you have these two numbers you're adding, they should both be positives. 49 plus 16 is 65. We're going to do our factor tree. I know 5 goes into it because 5 goes into anything that ends in a 5 or 0. So this is 5 times 13. 5 is a prime number, it doesn't break down. 13 is a prime number that doesn't break down. So this is our final answer. Let's do one more distance formula. We want the distance between the point -4, 3 and 2, -1. So again, big square root. Make sure you don't lose the big square root as you work through the problem. We're going to plug in our x's. I'm going to do 2 minus that's in the formula. The other x value is -4. Since we started with the 2 on the x's, we have to start with its partner y, -1, minus in the formula, positive 3. This 2 minus -4 turns into plus a positive, so we have 6 squared plus -1 minus 3 turns into plus a negative, so that's a -4 squared. 6 squared, 6 times 6 is 36. -4 squared, -4 times -4 is a positive 16. 36 plus 16 will give us the square root of 52. And we already broke down 52. We said that 2 goes into it 26 times. 2 went into 26 13 times. We have a pair of 2's, so the 2's go out, just one of them. Lonely 13 stays underneath, and that is our final answer. Again, you can go ahead and start on the homework. We'll work on this in class, clear up problems, talk about the notes. We're going to be on page 21 to 24. We're doing number 19 through 35, and for 19 through 35, that's all. Number 40, number 42, and then 60 through 71. And don't steer away from those large number problems. It doesn't mean they're more difficult. Those are simply review problems. Also in the review section, in the directions or next to the problem, it does tell you what section those are from, so you can always look back in the book to that section while you're working through those problems.